bosku, kita review lagi. We show interface error counter, frame, output errors, some kind, no, larger giants, auto, frame check sequence is 2 bytes, 4 bytes. Okay, Ethernet device use the CCNA CD. What is the number? First octet of class D. Class D. Wait. 224239. Full duplex. Frame check sequence. So the sign will be in switch, so it should be down. Translate between data format presentation. What is the Ethernet type for IPv6? 08DD 86DD. Okay. 5 fields of Ethernet header, preamble, SFD, source, destination, type, order size. Ethernet header type or length is 2 bytes. View the startup configuration. Show running config. Startup config. Save the configuration. Write memory. Copy running config. Startup config. MAC address table. Show MAC address table. Illegal frame for a unicast. Lowest level mode in user exec mode. Cisco command use type service. Password encryption type 7. What kind are common? USB and RJ45. MAC address 6 bytes, so 48 bits. Available less than indicate length 1500. View the running config. Show running config. We show the error count. Failed error CRC. Configure speed 100. Device attached to the switch can operate in switch full duplex. Ethernet header SFD. SFD is 1 byte. Source because it's Ethernet, so 6 bytes. The length of IP address in bytes, 4 bytes. What does a switch do in unknown unicast frame? Flood the entire interface except the original or the receiving port or interface. Global is indicated by what? Open bracket, config, close bracket, and then hashtag. What is the number of frames of the first octet class E? Class E is 240 to 55. Are all in the same collision domain? No. Comment to configure an IP address on an interface. IP address. IP address, the address, and then the subnet mask. Enter the global configuration mode. Configuration terminal. Config configuration. Configure terminal. Okay. In the output of show IP router's interface will be in router administratively down and down. Default Cisco console port setting parity is 0 or none. Which element does a switch use to learn and populate source MAC address? Hexadecimal C 12. In the revision will switch interface if connected to another device. Up. Ethernet preamble 7 bytes. Show internet variation received by device input errors. Display the configuration of its interface on router. Display the configuration on its interface. Show description. Show interface description. Okay. F15, D13, stop bits 1 bit. 1 bit. What to configure on the device? Running config and startup config. Enable secret use 5 encryption. Clear or dynamic address on a specific interface. Clear MAC address table. Clear MAC address table. Dynamic interface ID. Firewall has a filter like a PC host base. The first one of them are OUI, first 3 bytes. All devices connected to internet are in the same collision domain. What kind of cable is used to connect to RJ45 console port? Rollover cable. E14. Default will be removed after 5 minutes. Default Cisco flow control none. How long is a MAC address? 6 bytes. You use the keyword to execute in global configuration mode. Do. Configure full duplex on an interface. Full duplex. Duplex full. View the variable command question mark. What does MAC stand for? Media access control or medium? Up to you. Which show interface error counter minimum smaller than runs, which allow longer cable single mode or multi-mode single mode, with host to host communication. Host to host should be the transport, which command lets you configure multiple interface at the same time. Interface range. Device attached to an Ethernet hub must be operated in half duplex. Encrypt current and future password. Surface password encryption. Enable. No. Surface password encryption enable. No, just a surface. Okay. Provides process to process communication. Process to process should be application. A MAC address is written as hexadecimal character. MAC address 6 times 2, 12. What is the size of Ethernet header plus trailer? Header and trailer 18 bytes. What is the default speed setting of an interface? Auto. CSNA CD stand for carrier sense multiple access with collision detection. In Ethernet cannot send half duplex. Ethernet at layer 1. What is the binary pattern of the first octet of class B? 10XXXXX. What is the total size of Ethernet header plus trailer? Header plus trailer. 26 bytes. Default baud rate 9600. What's the internet time value for 86DD? Frame check sequence 4 bytes. View the startup configuration. Show startup config. Display the configuration on its interface on router. Display the configuration description. Show interface description. Okay, good. Now let's learn. We are in day 9, so we'll continue today. CCNA.
With data camp, you don't
let's do the
Welcome to
document learning CCNA, and then day 9 lab. Configure the hostname of R1, switch 1. Okay, let's do the R1 first. Where is the R1? This is switch. R1 CLI, enter, enable host conft hostname R1 first, IP address interface G00, IP address 172.16.255.254, and then 255.255.00, and then no shut, and then show IP interface to show IP interface brief. Okay, IP address IP Ethernet, good. And then exit. Okay, that's R1, and then switch 1. Or bigger matter. Go back to en show IP interface. Right. That's R1, and now switch 1. Switch 1 will do enable conft hostname switch 1, and then manually configure this on interface connected to other network device, not end host. Why should I manually do that? Okay, let's configure that. Switch to en conft hostname switch to configure a IP address for R1 PC1. Okay, PC1 config fast Ethernet. IP configuration should be 172.16.0.1. Okay, PC2 172.16.0.2. Okay, this one is 172.16.0.3. And then next one will be 172.16.0.4. Okay, good. And then configure the display on internet connect to other networking device, not the end host. Manually configure. Okay, switch one. Interface. F0 to show status. Show interface status. To show IP interface brief. Up. Okay. Let's do interface range F0 3 to 21, right? Shut down, and then exit. Do show IP interface brief. Okay, good. And then speed and duplex, so it's fast Ethernet. Interface range F01 to 2, duplex full, speed 100. Do show interface status full. Do IP interface brief. Show. Why is it done? No, shut. Show IP interface brief. Do show IP interface. We don't have to worry about that. Only worry about this. Do show IP interface brief. Interface range F01 to 2, duplex full, and then speed 100. Sit in range F03 to 21. Shut. Then exit. Right.
Jeremy's IT Lab. This is a free, complete course for the CCNA 200-301. Comment will configure.os connect to so this on R1 of route exec mode, R1. And you can see the doing the config. Remember, do lets me use the show command, even if assigned, so the method is 172 mask will be in device, switch 1 per second, because this is a gigabit duplex. There's no reason to use half duplex like a device attached to a hub. Next, let's configure.
Braces are drama. Invisalign is drama-free.
全新舒跑 Energy 电解质加牛磺酸，急速脉冲，舒跑能量饮。
Switch 1. Now, the last step, we don't have to do no shut IP interface brief. Okay, you can see the IP address we configured. The method is manual, the status is up, but the protocol is down. Although on a real Cisco device, I think this should be up, up. On Packet Tracer, it's down because I manually configured the speed and duplex on this interface without doing so on Switch 1's interface, but we'll fix that soon. That's a downside of using a simulator like Packet Tracer. Sometimes things don't behave like they should on a real device. Before moving on to Switch 1, I'll configure descriptions on R1's other interfaces to indicate that they are not in use. I'll use the interface range commands. Okay, let's check our config. Do show run. Here's the running config of the device, and here are the configurations of the interface, including speed to return to privileged exec mode. Now let's save the running configuration. Here on R, let's check if it was saved to the startup config. Show startup config. Here are the interfaces. To switch 1, I'll make the only configuration change we need to make on the PCs, configuring their IP addresses, which is R1 interface. PC order for the network. Now, click on Fastpass. I pre-configured the gateway. Let's go on PC 1. Click on Config, and notice I pre-configured the gateway, which is R1's address, because it's the router for the network. Now, click on Fast Ethernet 0, which is PC 1's network interface. PC 1's IP address is 172.25.255.0, Fast Ethernet 0, next 2.16, config in the subnet mask, enable, conf t, first the hostname, settings. No descriptions, but not routers, by the way. As you can see, all default settings. Let's configure that G. It's connected to R1, so description to R1. That's it. Now G02. Interface G02. Speed 1000, duplex full. It's connected to switch 2, so description to switch 2. Now, as for Fast Ethernet 01 and 02, they are connected to end hosts, so according to the lab instructions, I don't need to configure the speed and duplex. So I'll just configure descriptions. Interface range F01 to 2. Description to end hosts. To unused description do show not in use. Shutdown. Okay, let's check the configurations. Do show interface status. Shutdown. Focus we disabled. Configurations. Do show interface status. Okay, you can see the interfaces we disabled. Again, because I configured the duplex manually on G02, it's down at the moment, but will come up when we configure switch 2. Notice the speed and duplex we manually configured. This is also a problem with Packet Tracer. It says A-1000 and A-full, meaning it auto-negotiated the speed of 1000 and duplex of full, which is incorrect because we manually configured it. On a real Cisco device, this will say simply 1000. Now let's save the configuration. Config. Switch 2. Interfaces. Configurations we will make. So, I'll run through description to switch 1. The other interface. Not in use. Shutdown. Now let's check. Do show interfaces status. Once again, notice the speed of A-1000 and duplex of A-full. On a real Cisco device, this will be 1000 and full, without the A. And this time I'll just use write to save the configuration. Now let's check. Show startup config. Thank you for watching. Please subscribe to the channel.
Okay. Continue the day.
发烧让你全身疼痛不舒服？服用普拉疼止痛加强定，10分钟开始作用，有效缓解时。
Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment and share the video to help spread this free series of videos. Thanks for your help. Also, remember to download and use the Anki flashcards with the link in the description, which will help you very much in remembering what you have learned. Let's get started. In this video, we're going to take a look at the Internet Protocol version 4, known as IPv4 header. This is used at layer 3 to help send data between devices on separate networks, even on other sides of the world over the internet. This is known as routing. Originally, I planned this video to be a general introduction to routing, but in the end, I decided to split it up into separate parts. Let's take a look at what we'll cover in this video. We'll cover the IPv4 packet structure, or more accurately, the IPv4 header, which is used to encapsulate a TCP or UDP segment. Specifically, we will cover the fields of the IPv4 header. We already looked in detail at two fields of the header, the source and destination IP address fields, but there are quite a few more fields to look at. And that's all for this video. As I said, I originally planned to make this a long introduction to routing video. However, I don't want to make these videos too long. Already the shortest videos are at least 30 minutes, which is quite long, I think. So I decided to split up routing into more videos. This prevents the videos from getting too long, but also lets me go more in depth on each topic. So this video will focus exclusively on the fields in the IPv4 header, and then future videos will get more practical, with hands-on configuration in the CLI. Since we're going to look at the IPv4 header, let's review its position in a complete frame. So, the upper layers of the OSI model prepare some data to be sent to another device. It is encapsulated in a layer 4 header, typically using the TCP or UDP protocols, which we'll talk about in future lessons, with a layer 3 header, usually using the Internet Protocol, IP. This combination of data, layer 4 header, and layer 3 header is called a packet. Then, the layer 2 header and trailer are added, and this is called a frame. These units are called protocol data units, or PDUs. For example, the layer 3 PDU is a packet, and the layer 2 PDU is a frame. For this lesson, we'll focus on this layer 3 header, as it contains the information that is needed to route this packet to its destination. Note that, since we'll be focusing on layer 3 here, I'll usually be using the term packet, talking about routing packets, rather than frames. So, thanks to Wikipedia for this chart of the IPv4 header structure. As you can see, it's a bit more complicated than the Ethernet header. To be honest, I doubt that it will be necessary for you to memorize the exact structure of the header, the size of each field, etc. for the CCNA test, but I can't make any guarantees. I didn't make the test. What I recommend is just getting to know the purpose of each field of the header, which we'll cover now. By the way, if you're wondering how to read this chart, it's left to right, top to bottom. So, this is the first bit of the header, and this is the last bit of the header. So, let's quickly go through each field of the header. This is the first bit of the header, and this is the last bit of the header. So, let's quickly go through each field of the header so you're familiar with its purpose. First up is the version field of the header. For each field of the header so you're familiar with its purpose. First up is the version field of the header. Its length is 4 bits, half of 1 octet. Its purpose is straightforward. It identifies the version of IP used. Now, there are only two versions of IP in use. IPv4, which is simply identified with the value of 4 in this field, or 0100 in binary. The other version is IPv6, which is identified with the value of 6, or 0110 in binary. Now, you may wonder what happened to IPv5. Well, there was an experimental protocol called Internet Stream Protocol, which uses an Internet Protocol value of 5, but it was never publicly used. So you could say that's the lost IPv5. Now, we're focusing on the IPv4 header, so this field of the header will always have a value of 4. The IPv6 header has a different structure than the IPv4 header. So if the value of this field is 6, the rest of the header will also have a different structure. IPv4 header. So if the value of this field is 6, the rest of the header will also have a different structure. Next up is the Internet Header Length, or IHL field. It's also 4 bits in length, half of 1 octet. The final field of the IPv4 header, options, is variable in length. So this field is necessary to indicate the total length of the header. Here's an important part to remember. This field specifies the length of the header in 4-byte increments. For example, if the value in this field is 5, 5 times 4 bytes is 20, so that means that the length of the header is 20 bytes. The minimum value in this field is 5, which as I just said is equal to 20 bytes. That's the length of the IP packet without any IP options at the end, so it is equal to 20 bytes. The minimum value in this field is 5, which as I just said is equal to 20 bytes. That's the length of the IP packet without any IP options at the end, so an empty options field. The maximum value is 15, which is the maximum value of 4 bits. As you can see here, the value of the 4 bits are 1, 2, 4, and 8. Adding them up results in 15. So 15 times 4 bytes is equal to 60 bytes. That means the maximum length of the IP options field is 40 bytes. So an IPv4 header with no options field is 20 bytes in length, and that's the minimum length of an IPv4 header. And an IPv4 header with a maximum length options field, 40 bytes, has a length of 60 bytes, and that's the maximum length of an IPv4 header. Okay, that's the IHL field of the IPv4 header.
According to the UN.
Next is the DSCP field. DSCP stands for Differentiated Services Code Point. and the field's length is 6 bits. This field is used for QoS, quality of service. Basic QoS is a topic on the CCNA, so I will make a dedicated video about it later. Essentially, it is used to prioritize delay-sensitive data, such as streaming voice and video. If you're loading a web page and the internet is a little slow, it's not a big deal. However, if you're having a Skype call and there's terrible delay, or the audio and video keep freezing, it can totally ruin the experience. This field is used to identify which traffic should receive priority treatment. Next up is the ECN field, which stands for Explicit Congestion Notification and has a length of 2 bits. It provides end-to-end notification of network congestion without dropping packets. Normally in a network, if the network is super busy, if there is congestion, this is signaled by dropping packets. Normally in a network, it provides end-to-end notification of network congestion without dropping packets. Normally in a network, if the network is super busy, if there is congestion, this is signaled by dropping packets. The ECN field provides a way to signal a congested network without dropping packets. However, this is an optional field that requires both endpoints, as well as the underlying network infrastructure to support it. Next up is the total length field, and its length is 16 bits, or 2 octets, 2 bytes. It indicates the total length of the packet, including the IPv4 header and the encapsulated layer 4 segment, which includes both the layer 4 header and the data. This is different than the IHL field, which indicates only the length of the IPv4 header itself. This field indicates the length in bytes, not in 4-byte increments like the IHL field. So, a value of 20 in this field simply means 20 bytes. The minimum value in this field is 20, meaning 20 bytes, which is equal to a minimum size IPv4 header with no encapsulated data. The maximum value is 65,535, which is the maximum value of 16 binary bits, all set to 1. Let me just show you that calculation. Here are 16 bits, 2 octets, all set to 1. The first bit is equal to 1, then 2, then 4. When looking at next 96, the max 16 bits of an IPv4 packet. It is fragmented due to being too large. This field is used to identify which packet the fragment belongs to, so it can be reassembled again to make the original packet. All fragments of the same packet will have their own IPv4 header with the same value in this field, so they can be reassembled later. Packets are fragmented if larger than the MTU, which stands for Maximum Transmission Unit. The MTU is usually 1,500 bytes. Remember the maximum size of an Ethernet frame? I mentioned that the maximum payload size of an Ethernet frame is 1,500 bytes. So, these are fragmented if larger than the MTU 500 bytes. Remember the maximum size of an Ethernet frame? I mentioned that the maximum payload size of an Ethernet frame is 1,500 bytes. So, these are related. And one last point, fragments are reassembled by the receiving host. So, these are related. And one last point, fragments are reassembled by the receiving host. Next is the flags field, which is 3 bits in length. It is used to control and identify fragments. There are 3 bits, and which is 3 fragments are reassembled It is used to control and identify fragments. There are 3 bits, and they function like this. The first bit, bit 0, is reserved and always set to 0. Bit 1 is the don't fragment, or DF bit. If it is set to 1, it means that the packet should not be fragmented. Bit 2 is the more fragments, or MF bit. It is set to 1 if there are more fragments in the packet, and then set to 0 for the last fragment. Also, if the packet is a whole, unfragmented packet, the MF bit is set to 0, since there are no fragments. Next we have one more field related to packet fragmentation. That is the fragment offset field, which is 13 bits in length. This field is used to indicate the position of the fragment within the original unfragmented IP packet. This allows fragmented packets to be reassembled even if the fragments arrive out of order, since this field lets the receiver know the original order of the fragments. Next up is the time to live field, which is 8 bits in length. A router will drop a packet with a TTL of 0. So, this field is used to prevent infinite loops. If a poor routing configuration causes a packet to be continually sent around in a loop, never reaching its intended destination, if enough traffic like that accumulates, it could cause network congestion and eventually failure. This feature prevents that from happening, causing looped traffic to be dropped when the TTL reaches 0. This feature was originally designed to indicate the packet's maximum lifetime in seconds. In practice, however, this actually indicates a hop count. Each time the packet arrives at a router on the way to its destination, the router decreases the TTL by 1 until the packet reaches its destination, or the TTL reaches 0 and the packet is dropped. The current recommended default TTL is 64. Next up is the protocol field, which is also 8 bits in length. It It indicates the protocol of the encapsulated layer 4 PEU. Typically, this will be one of the following: TCP, which is indicated by a value of 6, or UDP, which is indicated by a value of 17. I haven't talked about TCP and UDP yet, but I will make a dedicated video about them later. For now, try to remember the protocol numbers of 6 for TCP and 17 for UDP. You might also see a value of 1, which is used for ICMP, the protocol ping uses. Another one to remember is 89, which is OSPF, which stands for Open Shortest Path First. OSPF is a dynamic routing protocol, which allows routers to learn routes to destination shortest path first. OSPF is a dynamic routing protocol, which allows routers to learn routes to destinations from their neighbors without OSPF is a dynamic routing protocol, which allows routers to learn routes to destinations from their neighbors without us having to manually configure the routes. We will cover OSPF in depth in this course, so for now just try to remember the protocol number of 89. If you're curious, you can check a list of protocol numbers at this page on Wikipedia. Don't worry about memorizing any others, but try to remember these 4.
6 TCP, 17 UDP, 1 ICMP, 89 SPF.
The included flashcards are extremely useful for remembering little facts like these. Next is the header checksum field, which is 16 bits in length. It is a calculated checksum used to check for errors in the IPv4 header. When a router receives a packet, it calculates the checksum of the header and compares it to the one in this field of the header. If the newly calculated checksum and the checksum in the IPv4 header do not match, it means that an error has occurred in transmission, so the router drops the packet. Note that this is only used to check for errors in the IPv4 header, not in the encapsulated data. IP relies on the encapsulated protocol to do that. Both UDP and TCP, the two layer 4 protocols most likely to be encapsulated, have checksum fields to check for errors in the encapsulated data. Okay, next up are the source and have checksum. Both UDP and TCP, the two layer 4 protocols most likely to be encapsulated, have checksum fields to check for errors in the encapsulated data. Okay, next up are the source and destination IP address fields, which I covered in detail
IP address is 4 bytes.
Already. As you already know, they are 32 bits in length each, as that is the length of an IPv4 address. The source IP address field indicates the IPv4 address of the sender of the packet. The destination IP address field indicates, which is optional and can be 0 bits in length if not used, or up to 320 bits, 40 bytes in length. This field is rarely used. However, if the IHL, Internet Header Length field, is greater than 5, it means that options are present. Here is a chart from Wikipedia showing the structure of the options field. You can check it out or read more online if you're interested, but for the purposes of CCNA studies, I don't think you need to worry about it. Okay, now we've covered all of the fields of the IPv4 header. It's a bit more complicated than the simple Ethernet header and trailer we already learned about, but hopefully you understand the purpose of each field now. For the purpose of the CCNA, I think the information presented in this video is sufficient, but of course feel free to read more. A simple Google search will give you many good resources. Also, don't forget to use the Anki flashcards to help you remember everything. Now let's go in depth and analyze a packet capture from Wireshark. I showed you Wireshark before, and it's an extremely useful tool both for learning and also in the real world to troubleshoot problems. This isn't a Wireshark course, but I will show you Wireshark at various points in this course, and if you have a lab with real Cisco equipment, or a virtual lab using GNS3, I highly recommend you use Wireshark to examine network traffic like this. It will really help you in your studies. But in either case, I will show you Wireshark packet captures in this course, so don't worry if you aren't able to use it yourself. So, I sent a ping between two routers. Notice under the info column it says echo ping request. I have selected the frame here, meaning the entire frame, and you can see down here that the entire I have selected the frame here, meaning the entire frame, and you can see down here that the entire frame is highlighted. These digits are a hexadecimal representation of the frame. Now I highlighted the Ethernet header, and down at the bottom you can see only the Ethernet header section of the frame is highlighted. Then I highlight the IP header, and at the bottom only the IP header section of the frame is highlighted. Then I highlight the packet's payload, which is Internet Control Message Protocol, or ICMP, the protocol used by ping, and you can see the payload highlighted at the bottom. In this video we're focusing on the IPv4 header, so let's expand the Internet Protocol version 4 information.
What's it like to learn math on Brilliant.org? Brilliant gets you hands-on to help you learn by doing.
Okay, so I've expanded the IPv4 header section and zoomed up a bit. And here you can see all of the fields we looked at in this video, except options. As I said, options are rarely used, and they aren't in this packet. First up, the version field. And you can see the binary bits 0100 on the left, and it shows you that means version 4. Next is the header length, which is the IHL field. It has a binary value of 0101, which equals 5. Remember, this field indicates the length in units of 4 bytes. So this value of 5 means a header length of 20 bytes. That is the minimum header length, and it is the length of an IPv4 header with no options field. Next up is the differentiated services field. And as you can see, Wireshark categorizes both the DSCP, differentiated services code point, and ECN, explicit congestion notification, indicates, it shows you in this video, for protocol used by ping, and you can see the payload highlighted at the bottom. You can see all this video we're focusing on the IPv4, so except option. So let's expand the Internet Protocol version 4 information. Here you can see all this packet, and it shows you that means version 4. Next is the header length, which is the IHL field. It has a binary value of 0101, which equals 5. Remember, this field indicates. Next up is the differentiated services field. And as you can see, Wireshark categorizes both the DSCP, differentiated services code point, and ECN, explicit congestion notification fields, under this section. Both are set to 0 as they are not being used. Next up is the total length. This represents the total length of the IP packet in bytes, including both the header and the ICMP data it encapsulates. The total length of the IP packet in bytes, including both the header and the ICMP data it encapsulates. So this 100 means that the total length is 100 bytes. Next is the identification field. This packet has an identification field of 5. It's not fragmented, but if it were fragmented, the other fragments belonging to this packet would also have a value of 5 here. Next up is the flags field. Notice that Wireshark also includes the fragment offset field under this section. The reserved bit is always 0. That's what not set means, by the way. I sometimes say set to 0 or set to 1. But another way of saying it is not set, which means 0.
1, 2, 3, 4. 1, 2, 3, 4.
Or set, which
4 bytes.
means 1. The don't fragment bit
4 bytes, and then we have 4 bytes, 12. We have 8.
isn't set, so this packet can be fragmented if necessary. The don't fragment bit isn't set, so this packet can be fragmented if necessary. The more fragments bit also isn't set, which is expected as the packet isn't fragmented. The fragment offset field is also 0, which is also expected in a packet that isn't fragmented. Next is the time to live field, which is set to 255, the maximum. Remember, the time to live field is 8 bits in length, and 255 is the maximum 8-bit value. The protocol is ICMP because I used ping. Notice the protocol value of 1, which indicates this. You can see the header checksum here. Remember, it's a 16-bit value. 0x indicates hexadecimal, and then each hexadecimal digit is equal to 4 bits.
4 plus 6 plus... No, 4 plus 4 plus 4, 12, 12 plus... hexadecimal 2. 12 plus 2, 14, 14 plus...
So 4 times 4 is 16, 16 bits. Here's the source IP address, and finally, the destination IP address. The standard ping command on a Cisco router will send 100-byte pings, which is why the ping I showed you wasn't fragmented. But I pinged once more using this command, ping 192.168.1.2, size 10,000, which will send 10,000-byte pings, much larger than the 1,500 bytes MTU. So this will cause fragmentation. As you can see here, there are a bunch of IP fragments. They all say reassembled in number 13. What is number 13? Well, it's this ICMP echo request right here. Now let's take a look at some of the IPv4 header fields in these fragments. Okay, so these are the details of just the first 2 fragments. First off, notice the total length of 1,500 bytes. So this 10,000 byte ping was divided up into 1,500 byte fragments, which is equal to the MTU size. Then notice the identification field of 1. This is different than the last packet I showed you, but notice that the value is the same for these 2 fragments. Then take a look at the flags. Each of them has the more fragments bit set, because neither of these is the last fragment in the packet. Also notice that each of them has a different fragment offset value, and that the first fragment has an offset of 0. Just one more thing. This time I sent a ping and set the don't fragment bit by adding the df bit option to the ping command. 100 bytes was used, so it was no problem that these packets weren't allowed to be fragmented. However, if I send pings that are larger than the NTU and set the df bit, you can see the pings fail. They were too large to be sent unfragmented, but also not allowed to be fragmented. Before moving on to today's quiz, let's review what we studied. That's it, video. Okay, let's move on to details you learned. First field of an IPv4 header.
Of the first field of an IPv4. Fixed binary value of the first field. That version
0001.
0010. So it's
D.
wait. What is the value of the first field of an IPv4 header? It's 4, right?
D 0100. Answer is D. Is about an IPv00. It has a value of 0. A. D. Used by 1 and 3. A. The IPv4 header checksum field checks for errors. B. The encapsulated protocol, for example TCP or pause the videos. B. The encapsulated elf data. A. Option IHL.
Option.
Pause the video. Options length and packet. Which bit will be set to 1 on all IPv4 packet fragments except the last fragment? C. Don't fragment. More fragments bit of a bit IPv4 header. To help you remember, I think the flashcards are router. The video. Leave.
Let's do the flashcard. Date and flashcard IPv4 header. Let's do it. Version field is 4 bits. A value of version 0010. Yeah. 0110. E blah 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 header length. Internet header length. Internet header length is bits in length. 4 bits. There is the length of header in 4 bytes increment. The minimum value of IHL field 5. Maximum value of IHL field 15. 10 times 4. 15. What is the maximum length of IPv4 header? 20 bytes. Oh wait, I bet it's 25, 15 times 4, 600 bytes. 60. Minimum length 20 bytes. Differentiated surface per code point. Internet header length. Differentiated surface code point. Okay. Referring to Prototype delay sensitive DSCP, ECN, explicit congestion notification. Explicit congestion notification 4 bits, 2 bits. Which field provides end-to-end notification of 1? ECN. Total length field is blah 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 bits in length. Total length 13 bits, 16 bits. Which field is the total length of the packet? Total length. Minimum value of total length field 0, 20. Maximum value of total length field 65535. Differentiated surface code point. The SCP field is 6 bits. ECN conjugation notification. Explicit. The identification field is 4 bits. 16 bits. ECN field is 6 bits. 2 bits. Which field is used to identify which packet a fragment belongs to? Identification. All fragments of the name will have the same value in the identification field if they are larger than the MTU. The total length field is 16 bits in length. Minimum value of total length field 20 byte. Yeah, 20. What is maximum transmission unit? MTU is 1500 bytes. The flag field is 3 bytes. Bits. Unfragmented will always have the more fragment bit set to 0. IPv4 flag field bit first bit. Yeah, bit 0. The identifier field is 16 bits. Explicit conjugation notification. ECN is 6 bits, 2 bits. IPv4 header flags field bit number 1. Number 2. DF bit is done fragment bit, more fragment bit. Offset is 16, 8 bits, 13 bits. Which field is used to indicate the position of the memory within an fragment? Offset field, fragment offset. The TTL field is 8 bits. The recommended default 64. TTL of 0. TTL. Time to live. Protocol field is 6 bits, 8 bits. ECN 2 bits. Which field indicate the protocol of the encast? Which field? Type. Protocol. TCP 7, 6, 6 TCP, 17 UDP, 1 is ICMP is 1, OSPF 89, checksum field is 16 bits, and the fragment offset field is 13 bits, which we need to checksum source IP address is 32 bits, option field is 0, maximum is 60 times 8, 40 times 320 bits. The protocol field is 8 bits, which will indicate the protocol of encapsulated protocol. IPv4 TCP 6, a value of 4 or 0100. IHL is IHL 4 bits, minimum value of IHL field 15, minimum 5, maximum length of IPv4 header, maximum length of 60 bytes, recently parameter DSCP, IP for header version is 4 bits. PIHL and the length of header in 4-byte increment. A value of a version indicate version 60110. Minimum length IP for header 20 bytes. The SCP is 8 bits, 6 bits, which will provide end-to-end notification of network ECN. The SCP field is 6 bits, which field is into element of packet fragment belong to identification. Total length is 16 bits. Maximum value of total length field. Maximum value total length is 65535. Internet header length. Differentiated service code point. All fragments of the same packet will have the same value in the identification. MTU 1500 bytes. And fragment will have more one set to 0, which field indicate the total length of the packet. Total length. Flags bit 0 reserve. Bit 2. And if they are larger than MTU, identification field is 8 bits, 16 bits. Maximum value of total length field 65535. Minimum, not maximum. The identification field is 16 bits. Maximum value of total length field. Total length 20 bytes. Address is an explicit congestion notification. Address DF down fragment bit. Which field is used to indicate the position of the fragment with fragment offset. The TTL 64. Flags is 3 bits. Trap the packet with a TTL of 0. ECN is 2 bits. Time to live. Maximum transmission unit. Value of 6 TCP. 89. Offset field is 16. 13. 17 UDP. Is 13 bits, which we need to prevent infinite TTL to check the error in the header section. DF down fragment is 1. TTL is 16 8. Source IP address 30-bit 2. TTL is 8 bits. 89 OSPF. UDP is 17. More fragment bit. Destination IP address field is 32 bits. Maximum length of option is 40 bytes or 320 bits. Value of 1 ICMP. Protocol field is 16 bits, 8 bits. ICMP 1. Protocol field is 8 bits. Value of 6. Checksum field 16 bits, which will indicate the protocol of the SQM encapsulated protocol. Minimum length of option field 0. Identification table field is 16 bits. DSCP field is 6 bits. Fragment offset is 13 bits. TTL field is 8 bits. Minimum value of total length field. Minimum value of total length 20 bytes. Protocol field is 8 bits. Okay, good. Berapa? Bisa satu lagi.
今年大荧幕最爽体验。预售票热卖中，致命威胁，双王合体，开战到底。
Kong just got an upgrade.
哥吉拉金刚新帝国，3月27周三大荧幕开战。
If you want to learn Python for a career in data science, IT, or engineering, then you need the complete Python bootcamp.
Welcome to Jeremy's IT Lab. This is a complete course for the CCNA, Cisco Certified Network Associate exam. In this video, we will cover routing fundamentals, a very important topic to understand for the CCNA exam. In the Ethernet LAN switching videos, we looked at how switches forward frames to their proper destination. The process routers use to forward packets to their proper destination is different, and that's what we'll look at in this video. Here's what we'll cover in this video. First, I'll answer the question, what is routing? Then we'll look at the routing table on a Cisco router. Switches have MAC address tables, and routers have routing tables. It's very important that you know how to read a router's routing table. Specifically, we will look at two types of routes found in a routing table, connected and local routes. We will also look at routing fundamentals, specifically route selection. In a router's routing table, they will usually have a variety of routes. So how does the router select the correct route for a packet? We'll discuss that in this video. I want to emphasize that this lesson is extremely important for the CCNA and for learning networking in general, and so is the next video. So take it step by step, take notes, and ask questions if you need help. After covering all of the material, I will also show a one-slide review of everything in this video, so I hope that will help you review and remember what you learn. Let's get started. So, what is routing? Well, when a router receives a packet, it's the router's job to forward it, to send it to the correct destination. That's where routing comes in. Routing is the process that routers use to determine the path that IP packets should take over a network to reach their destination. And routers store routes to all of their known destinations in a routing table, which we'll look at soon. As I mentioned before, switches keep a MAC address table with their known destination MAC addresses. And routers keep a routing table with their known destination networks. When routers receive packets, they look in the routing table to find the best routes to forward that packet. There are two main routing methods that routers use to learn routes. One is dynamic routing, in which routers use dynamic routing protocols such as OSPF to share routing information with each other automatically and build their routing tables. We will cover dynamic routing protocols such as OSPF later in the course. Another type is static routing. In this case, a network engineer or admin manually configures routes on the router. We will cover static routing in the next video. In this video, we're going to cover a kind of route that doesn't fit into either category. Now, what exactly is a route? In this video, we're going to cover a kind of route that doesn't fit into either category. Now, what exactly is a route? Basically, it's an instruction to the router. A route tells the router, to send a packet to destination X, you should send the packet to next hop Y, and next hop means the next router in the path to the destination. Or if the destination is directly connected to the router, send the packet directly to the destination. Or if the destination is the router's own IP address, receive the packet for yourself, don't forward it. This is how the routing table works. It's a set of instructions like this. To demonstrate routing in this video and the next one, we will use this example network. Actually, in this video, we will only look at one small part of this network. In the next video, we will use the entire network. But first, let me introduce the network. There are 4 routers connected together, and they represent a WAN. WAN stands for Wide Area Network, a network that extends over a large geographical area. For example, each of these 4 routers could be in different cities or even different countries. And then, connected to R1 and R4, there are 2 LANs, local area networks. I'm only showing one PC at each LAN, but let's say each of these LANs is a different office in a different city, so really there are more hosts in each LAN. R2 and R3 probably should have their own connected LANs too, but just to keep the diagram a bit cleaner, I'm not showing them here. Now let's probably should have their own connected LANs too, but just to keep the diagram a bit cleaner, I'm not showing them here. Now let's look at the IP addresses each device will be using. For this LAN connected to R1, the network is 192.168.1.0/24, and R1's G02 interface IP is .1, and PC1's IP is .10. Then this WAN connection between R1 and R2 is 12.0/24. R1 G01's IP is .1, and R2 G00's IP is .2. This WAN connection between R1 and R3 is 13.0/24, with R1 G00 as .1 and R3 G00 as .3. The WAN connection between R2 and R4 is 24.0/24, with R2 G01 as .2 and R4 G00 as .4. Then the final WAN connection between R3 and R4 is 34.0/24, with R3 G01 as .3 and R4 G01 as .4. Then the LAN connected to R4's G02 interface is 192.168.4.0/24, with R4 G02 as .4 and PC4 as .10. Notice that I made all of the router IP addresses the same as their name. All of R1's IP addresses are .1. R2's IP addresses that I made all of the router IP addresses the same as their name. All of R1's IP addresses are .1, R2's IP addresses are .2, R3's are .3, etc. Don't expect IP addresses like this in real networks, but in lessons and labs, I will often use simple addressing schemes like this to make it easier to understand. In the next video, we will configure static routes on the routers to allow PC1 and PC4 to communicate with each other over the network. This video will focus on two types of routes automatically added to a router's routing table, not dynamic routes or static routes. Okay, before looking at routes, let's configure the IP addresses. I'll just show the configurations on R1, since that's the router we'll be focusing on in this video. First, I configured its G00 interface with IP address 192.168.13.1, 255.255.255.0, and then enabled it with no shutdown. Then I configured G01's IP address. Notice that while I was still in interface config mode for G00, I used the interface G01 command directly, without returning to global config mode first. There is no need to use exit to return to global config mode before entering interface G01. You can use the interface G01 command directly from interface config mode. I then configured G02 as well. To confirm, I used show IP interface brief, and you can see the IP addresses I just configured. Of course, I configured the other router's IP addresses too, but for the sake of time, I won't show them here. As I said, in this video, we'll just focus on R1. Now let's take a look at R1's routing table. The command is show IP route. It displays the router's routing table. And here is the output. There are two main sections to the output, the codes at the top and the actual routes at the bottom. The codes legend in the output of show IP route lists the different protocols which routers can use to learn routes, as well as the codes that represent the output of show IP route lists the different protocols which routers can use to learn routes, as well as the codes that represent them in the routing table. I've highlighted two in blue here. The first is L, which means local. This code is used for routes to the actual IP address configured on the router's interface, and these routes will have a /32 mask. If you look at the routes below, notice there are three routes with L that I've highlighted in blue, one for each of R1's interfaces. Then there is the C code, which means connected. These are routes to the network the interface is connected to, with the actual. Then there is the C code, which means connected. These are routes to the network the interface is connected to, with the actual. Then there is the C code, which means connected. These are routes to the network the interface is connected to, with the actual net mask configured on the interface. Notice there are also three routes with the C code in the output below. So even though we haven't configured any routes yet on R1, it already has 6 routes. When you configure an IP address on an interface and enable it with the no shutdown command, 2 routes per interface will automatically be added to the routing table, a connected route and a local route. Earlier, I mentioned that there are 2 main types of routing, dynamic routing and static routing. These connected and local routes, however, are neither. They are simply added automatically when an interface is configured. These are the routes we will focus on in this video. Okay, let me explain dynamic routing and static routing. These connected and local routes, however, are neither. They are simply added automatically when an interface is configured. These are the routes we will focus on in this video. Okay, let me explain these routes in more detail. So I've highlighted 2 of the routes, one connected route to 192.168.1.0/24, and one local route to 192.168.1.1/32. So a connected route is a route to the network the interface is connected to. R1 G02's IP is 192.168.1.1/24. What do the red and blue numbers mean here? Well, because it's a /24 address, the first 24 bits, the first 3 octets, are the network portion of the address. I've highlighted that portion in red. Then the last 8 bits, the last octet, is the host portion of the address, and I've highlighted it in blue. When you change that host portion to all zeros, the result is 192.168.1.0/24. And notice, that's the destination of that connected route. It's a route to that network. So this provides a route to all hosts in that network. For example, 192.168.1.10.100.232, etc. Any address in that .0/24 range. Look back up at the routing table, and notice that the route says 192.168.1.0/24 is directly connected, Gigabit Ethernet 02. So, R1 knows, if I need to send a packet to any host in that network, I should send it out of G02. Okay, that's the connected route. Next, let's look at the local route in more detail. A local route is a route to the exact IP address configured on the interface. A /32 netmask is used to specify the exact IP address of the interface. /32 means that all 32 bits are fixed, they can't change. So, even though R1's G02 is configured as 192.168.1.1/24, the local route is to .1/32, which specifies only that single address. It doesn't include 192.168.1.2, for example. So with this route, R1 knows if I receive a packet for the local route is to .1/32. Route 2 is configured as 192.168.1.1/24. The local route is to .1/32, which specifies only that single address. It doesn't include 192.168.1.2, for example. So with this route, R1 knows if I receive a packet for this IP address, the message is for me. It's to my own IP address. Just to make things clearer, let me show it like this. /24 means that the net mask is 255.255.255. They can't change. 68.1.0/24. That means that if R1 receives this begins with, so R1 would forward the packet out of G02. 2.1, however, does not match with this packet. The term match is very important, and I will use it a lot in this video and others, specified in the route. So the route matches the destination IP. Because it's /32, then 192.168.1.1. No other IP when we configured IP addresses on its interfaces. Now let's look at another fundamental concept, route selection. So R1 has a connected route to 192.168.1.0/24 and a local route to 1.1/32. Let's say R1 receives a packet and the destination IP is 192.168.1.1. Can you see the problem here? A packet destined for 1.1 is matched by both routes, 192.168.1.0/24 and .1/32. So which route will R1 use for a packet destined for 1.1? Will it send the packet out of G02, or will it receive the packet because the packet is for R1 itself? The answer is, it will choose the most specific matching route. So I explained what a matching route is. Let's see what most specific means. The route to 192.168.1.0/24 includes 256 different IP addresses, from 192.168.1.0 to .255. On the other hand, the route to 1.1/32 includes only one IP address, 192.168.1.1. It specifies just one IP address, not 256 different IP addresses. So, this route is more specific than the /24 route. So, when R1 receives a packet destined for 192.168.1.1, it will select the route to 1.1/32. So, R1 will receive the packet for itself, rather than forward it out of G02. That's the purpose of local routes. They tell the router, keep the packet, don't forward it. This means R1 will de-encapsulate the packet and look at the contents inside, because the contents are addressed to R1 itself. So, to summarize, the most specific matching route means the matching route with the longest prefix length. Both parts of that statement are important. The route must match the packet's destination, and it also must have the longest prefix length out of all the matching routes. That is the route that the router will use for the packet. Now let me point out these statements here in the output of show IP route on R1. You might have noticed them and wondered what exactly they mean. The top one says 192.168.1.0/24 is variably subnetted, 2 subnets, 2 masks. What exactly does that mean? Well, first of all, it's important to know that these 3 lines are not routes. They mean the following. The first line, 1.0/24 is variably subnetted, 2 subnets, 2 masks, means that in the routing table, there are 2 routes to subnets that fit within the 1.0/24 class A network, with 2 different subnet masks, those being /24 and /32. The other 2 mean the same thing for their respective networks. To really understand these statements, you have to understand what a subnet is, but we haven't covered subnets yet in the course. We will cover subnetting soon, in another video. For now, I just wanted to point out that these 3 lines are not routes, so you don't get confused by them. Generally, you can ignore this output in the routing table, and just focus on the routes themselves.
鼻子不通，头昏脑胀，转不动，轻轻一喷，5分钟快速缓解，欧治鼻。
Now let's look at a few examples to practice route selection. R1 receives a packet destined for 192.168.1.1. Looking at its routing table, which route will it select for this packet? And what will it do with the packet? If you want, you can pause the video now to think about the answer yourself. So we have to find the most specific matching route in the routing table. This first packet is destined for 192.168.1.1, and when R1 checks its routing table, it will see that the most specific match is this one, to 192.168.1.1/32. It is a local route, so R1 will receive the packet for itself. Note that this packet matches 2 routes in the routing table, the route for 1.0/24 and the route for .1/32. But the /32 route is more specific, so it will be selected. For itself. 68.1.1/32. It is a local route, so R1 will receive the packet for itself. Note that this packet matches 2 routes in the routing table, the route for 1.0/24 and the route for .1/32. But the /32 route is more specific, so it will be selected. Here's another example. Packet 2 has a destination IP address of 192.168.13.3. Which route will R1 select for this packet? And what will it do with the packet? 192.168.13. Here's another example. Packet 2 has a destination IP address of 192.168.13.3. Which route will R1 select for this packet? And what will it do with the packet? The most specific matching route, actually the only matching route for this packet, is this connected route to 13.0/24. So R1 will send the packet to the destination, which is connected to the G00 interface. Here's a third packet, destination IP 192.168.1.244. What will R1 do with this packet? The only matching route is this one to 1.0/24, so R1 will use this route to forward the packet. It's a connected route, so R1 will send the packet to the destination, which should be connected to that interface. And here's a fourth packet, destined for 192.168.12.1. What will R1 do with this packet? There are two matching routes, but the most specific one is this local route for 192.168.12.1/32. So R1 will receive the packet for itself. Okay, let's do one more practice question. Packet 5 is destined for 192.168.4.10. What will R1 do with this one? Because there are no matching routes in the routing table, R1 will have to drop this packet. Unlike switches, which flood frames if they don't know where the destination is, routers do not. Routers never flood packets. If the router doesn't have a route to the packet's destination, it will drop the packet. Okay, now let's try to review everything in this video in one slide. This will be just a wall of text, but hopefully it will help you review what we learned in this video. Route. Example O, by code L in the route E32 /20 route that MAC table entry destination is the matchable to 4 no concepts you reviews we covered in this video. I introduced the concept of routing, the router, an interface bit. Routing. To test your apps configured on a router interface, will two routes on the route to the examine R1's routing table. What will it do when it receives a packet destined for 192.168.3.25? 192.168.3. Okay, the answer is B. It will receive the packet for its.
But it's 13. I think it's a mistake. It should not be 13. But
Self. Our local route to 192.168.3.25 for 3. Which of the following statements about the behavior of routers and switches are true?
router, switch, router, drop packet, so BNC.
Select unicast. The routes are automatically added to the
L and C or CNA.
Routing table. IP router and IP address. Examine R1's routing table below.
How many routes to the destination? 10, 0, 1, 23. Two. Should be C.
Below. 10.0.1.0/2032. To another. Please click the join button. See Scott Zahar and on YouTube. So I really appreciate the support. This video with others.
Only 16. Let's do it. Router the destination in the routing table. With router receiver in the routing table. Static route. Dynamic route. The next router in the path is called the next hop. Show the routing table. Show routing table. So IP route. What does C? Connected. L local. Which two routes are automatically added to the L and C? R is a route to the actual IP address configured on the local. And then to the network, then it's connected. If a packet is matched with the most specific one. Most the matching route with the longest matching bit. Mask maybe? Yeah, longest. What will a router do if none of its routes match? Drop the packet. Local routes use a prefix length of 32. What prefix to connected route use? Follow the net mask. Show IP route. The next router in the next hop. More specific, the matching route with the longest prefix length. destination in the routing table to the actual local connected. Okay, they look in the routing table. Static, when added to the routing when you can local and connected. But if drop the packet, show IP route is added to the routing table by the protocol. Dynamic, local, multiple route is longest matching prefix. More specific. Log to the network is connected. Local route 32 connected. Use follow the configured prefix. Good.
So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching. Welcome to Jeremy's IT Lab. This is a complete course for the CCNA, Cisco Certified Network Associate exam. In this video, we will cover static routing, a very important topic to understand for the CCNA exam. In the previous video, we looked at the basics of routing, how routers decide where to forward packets. And we looked at two types of routes, local routes and connected routes. Those routes are automatically added to a router's routing table when you configure an IP address on an interface. Local routes provide a route to the router's own IP address, and connected routes positions that aren't directly connected to the router itself. Local and connected routes aren't enough. Today's topic, static routes, enable routers to send packets to remote destinations that aren't directly connected to the router itself. Here's what we'll cover in this video. First, we'll briefly review connected and local routes, and how CLI of Cisco routers. Finally, I will also explain the configuring IP addresses on the routers and checking their routing tables. In the last video, I showed R1, so for this video, let's start from R2. I configured IP addresses on G00 and G01, and enabled both interfaces. Remember, if an interface is disabled, the connected and local routes for that interface won't appear in the routing table. Now, before I show the routing table, I want you to think about what routes there will be in the routing table. There should be one connected route and one local route per interface, so a total of 4 routes. Remember, these routes are added automatically, while the 8.12 addresses not showing all of the different codes listed at the top of the output. Remember, C means connected and L means local. Anyway, as expected, R2 has 2 connected routes, one to 12.0/24 and one to 24.0/24. Also, it has 2 local routes, one to 12.2/IP addresses, and destinations in its connected networks, but it doesn't know how to reach destinations in remote networks. Destinations in the 192.168.12.0/24 and 24.0/24 networks. If R2 receives packets destined for hosts in these other networks, it will have to drop them. R2 doesn't know where it should send them. And here's R3's configurations. 192.168.13.3/24 on its G00 interface, and 34.3/24 on G01. So which routes will it have in its routing table? And 34.3/24, 192.168.13.3/24 on its G00 interface, and 34.3/24 on G01. So which routes will it have in its routing table? It's how to reach its own IP addresses. You know by now, it has 2 connected and 2 local routes. So like on R2, R3 knows how to reach its own IP addresses. Those of 13/3 the nation would have to use. So how many routes will it have in its routing table? The answer is 6. 3. R4 network receives so it 192.1 and PC4 to communicate. Notice that I've colored the interface labels for each device, and their defaults move through the network. ETH0, Ethernet 0. These colors will make things easier to understand as I demonstrate how packets move through the network. 1 and PC4 can send packets directly to destinations in their connected network. PC1 is connected to 192.168.1.0/24, so it can directly communicate with other hosts in that network. However, to send packets to destinations outside of their local. So these are the configs on PC1 and PC4. In Linux, the interface configurations are stored in a text file that you can edit. On PC1, for example, there is the line address 192.168.1.10/24, which configures the IP address as 1.10 with a prefix length of /24. And below that is the default gateway configuration, gateway 192.168.1.1. So to send packets to destinations outside of its local network, PC1 will send packets to R1. The default gateway configuration is also called a default route. Basically, It's a route to O.O.O.O/O. All netmask bits are set to 0. None of the bits in the address are fixed. O.O.O.O/O includes all addresses from O.O.O.O to 255.255.255.255. It's a route that includes everything. Remember the concept of most specific matching route in the previous video? Well, the default route is the least specific route possible, because it includes all IP addresses. O.O.O.O/O includes over 4 billion IP addresses. On the other hand, a /32 route, like a local route, is the most specific route possible, because it specifies only one IP address. For example, 192.168.1.1/32 specifies only one IP address. So the default route says, if there aren't any more specific matches for this packet, don't drop it, send it via this route instead. Later, we'll see how to configure a default route on a Cisco router and what it can be used for. But for now, just understand how it works for end hosts like PC1 and PC4. End hosts usually have no need for any more specific routes. It works for end hosts like PC1, a default route on a Cisco router, and what it can be used for. But for now, just understand how it works for end hosts like PC1 and PC4. End hosts usually have no need for any more specific routes. They just need to know, to send packets outside of my local network, I should send them to my default gateway. So if PC1 wants to send a packet to PC4, the source IP address in the IP header is 192.168.1.10, PC1's IP, and the destination IP is in the Ethernet header. This is where you can start to really understand what will the source and destination MAC addresses be in the Ethernet header. This is where you can start to really understand the role of layer 2 and layer 3. At layer 3, PC1 wants to send a packet to PC4, so the destination is PC4's IP, 192.168.4.10. However, it has to first forward this packet to its default gateway, R1. So it will encapsulate the packet in a frame, and the destination MAC will be R1G02's MAC address. Now, how does it know R1G02's MAC address? To learn it, PC1 will first send an ARP request to 192.168.1.1, R1G02's IP address. I will show this part of the process in more detail in the next part of the course, called Life of a Packet. To keep things a bit simpler in this video, let's just assume each device already knows its neighbor's MAC addresses. I won't show all of the ARP exchanges. So, PC1 sent that frame to its default gateway, R1. When R1 receives the frame, it will de-encapsulate it, meaning it will remove the layer 2 header and trailer, and look at the inside packet. It will then check the routing table for the most specific matching route. It has to make a decision about what it will do with this packet. So here is R1's routing table at the moment, just connected and local routes. Do any of these routes match the destination IP of the packet? No, R1 has no matching routes in its routing table. So what will it do with the packet? It has no choice but to drop it. In its current state, R1 doesn't know how to properly forward the packet. To forward it, R1 needs a route to the destination network, 192.168.4.0/24. Remember, routes are instructions. R1 needs a route to say, to send a packet to destinations in network 192.168.4.0/24, forward the packet to next hop Y. Now we know the destination, the 4.0/24 network, but what should be the next hop? What is the next router in the path to the destination? Actually, there are two possible paths that packets from PC1 to PC4 can take. One is the path via R3, PC1 to R1 to R3 to R4 to PC4. The other path is the one via R2, PC1 to R1 to R2 to R4 to PC4. In this video, we will use the path via R3, not the path via R2. So we won't actually use R2 much in this video. The reason I included R2 in the diagram is that I wanted to demonstrate that if there are multiple paths to the destination, you can choose which one the routers should use. Now it is possible to configure the routers to use these multiple paths differently. Instead of choosing one path, they can load balance between path 1 and 2. That means some packets will take path 1 and some will take path 2. Or they could, for example, use path 1 as the main path and path 2 as a backup path. You will learn about these techniques later in the course. In this video, we will only use path 1, the path via R3. Now, to ensure PC1 and PC4 4 can communicate with each other, it's not just R1 that needs another route. Each router in the path needs two routes, a route to 192.168.1.0/24, PC1's network, and a route to 4.0/24, PC4's network. This ensures two-way reachability, which means that PC1 can send packets to PC4, and PC4 can send packets to PC1. If, for example, all routers had routes to 192.168.4.0/24, but not 1.0/24, PC1 would be able to send packets to PC4, but PC4's replies wouldn't be able to reach PC1. R4 would drop the reply because it would have no route that matches destination 192.168.1.10. So, we want two-way reachability. It's worth noting that routers don't need routes to all networks in the path to the destination. For example, R1 doesn't need a route to 192.168.34.0/24. It just needs to know, to send packets to 4.0/24, I should send the packets to R3. R3 will take care of the packets after that. And likewise, R4 doesn't need a route to 192.168.13.0/24. R4 just needs to know, to send packets to 1.0/24, I should send the packets to R3. R3 will take care of the packets after that. Okay, continuing on, R1 already has a connected route to 1.0/24, and R4 already has a connected route to 4.0/24. However, the other routes must be manually configured using static routes. Before we get into actually configuring static routes, let's plan out the routes we will configure. Here's a chart of the routes R1, R3, and R4 need to allow PC1 and PC4 to communicate with each other. In blue are R1 and R4's connected routes. Note I listed the next hop as connected. Then in red are the static routes we have to configure. I will show the answers, but before that I want you to pause the video and think about what the next hop IP address should be for each route. Now let's check. For R1 to send a packet to the 4.0/24 network, what is the correct next hop IP address? Remember, we're using the path via R3 for this video, not the path via R2. The answer is 192.168.13.3. The IP address of R3's G00 interface. R1 has a connected route to 192.168.13.0/24, so it knows how to reach 13.3. It can then use that IP address as a next hop to send packets toward the 4.0/24 network. Okay, next one. What next hop IP should R3 use to send packets to the 192.168.1.0/24 network? The answer is 192.168.13.1, R1's G00 interface. And how about 4.0/24? It should send packets to 192.168.34.4, R4's G01 interface. Finally, what next hop should R4 use to send packets to the 1.0/24 network? The answer is 192.168.34.3, the IP address of R3's G01 interface. Okay, we've planned the static routes we need to configure. To allow PC1 and PC4 to communicate with each other over the network, let's configure these static routes on R1, R3, and R4. First up, let's configure R1's route to 192.168 route, followed by the destination network IP, netmask, and next hop IP. So for R1's route to the 4.0/24 network, the command is this: IP route 192.168.4.0, 255.255.255.0, 192.168.13.3. That's it. Fairly simple. I then checked R1's routing table. Notice I highlighted the code for static routes. It's S, as you might have guessed. And I've also highlighted the route itself in the table. Notice in square brackets there are two numbers, 1/0. What do those numbers mean? They are the route's administrative distance and metric. We will cover these concepts later in the course. Don't worry about their meaning for now. I'm just pointing them out in case you're curious what those numbers are. Okay, that's all we have to configure on R1. It now knows that, to reach PC4's network, it should forward packets to 192.168.13.3, R3. Next up, R3. It needs to forward packets to 192.168.13.3, R3. Next up, R3. It needs two routes, 1 to 1.13.3, R3. Next up, R3. It needs two routes, 1 to 1.0/24 and 1 to the video 24 network, with R1 as the next hop. 3's routing table 2. Again, you can see both routes there with their next hop IP addresses. To reach 192.168.1.0/24, send packets to R1. To reach 4.0/24, send packets to R4. And finally, let's configure R4's route to the correct command 5.255.2 as the next hop area for PC1 and PC4 to communicate. Let's test it out and see if they can actually communicate with each other. To test it out, I pinged from PC1 to PC4, and the ping was successful. As I've highlighted, it says 5 packets transmitted, 5 packets received, 0% packet loss. If the ping is successful, that means there is two-way reachability. PC1 can reach PC4, and PC4 can reach PC1. If PC1 could reach PC4, but PC4 couldn't send replies back to PC1, the ping wouldn't work. So the configurations were successful. Now, let me briefly show how a packet from PC1 wouldn't. If PC1 could reach PC4, but PC4 couldn't send replies back to PC1, the ping wouldn't work. So the configurations were successful. Now, let me briefly show how a packet from this travels through the network. We will examine this process step by step in the Life of a Packet video coming up soon, but this is just a preview. You don't have to think too much about the process yet. As you saw earlier, when PC1 sends a message to PC4, the layer 3 destination is PC4's IP address, 192.168.4.10. However, at layer 2, the destination is PC1's default gateway, which is R1's G02 interface. Now R1 has the packet, and it's R1's job to forward it to the next hop, R3. To do so, it encapsulates the packet in a new Ethernet frame. This time, the destination of the frame is the next hop's MAC address, so the MAC of R3's G00 interface. Now R3 has the packet and must forward it to the next hop, R4. To do that, it once again encapsulates the packet in a new Ethernet frame, and the destination of that frame is the MAC of R4's G01 interface. Now R4 has the packet, and since it's directly connected to the destination network, it can forward the packet to PC4. It does that by encapsulating the packet in a frame with PC4's MAC as the destination. This is the only time in the journey that the destination IP and MAC are of the same device. This is the only time in the journey that the destination IP and MAC are of the same device. The destination IP is PC4's IP, and the destination MAC is PC4's MAC also. This process is very important to understand, but as I said, we will cover it step by step in another video. For now, just understand that the source and destination IPs of the packet do not change throughout the journey. But each time the packet is de-encapsulated and re-encapsulated, the source and destination MAC addresses are different. Okay, now I want to introduce another option when configuring static routes. We haven't configured any routes on R2 yet, so I'll just use it for this demonstration. When configuring static routes, instead of configuring a next hop, you can configure an exit interface instead. That means you specify which interface this router should send the packets out of, rather than telling it the actual IP address of the next hop. For example, if R2 wants to send packets to the 192.168.1.0/20, it should send the packets to R1. What interface should R2 send packets out of to reach R1? G00, because that interface is connected to R1. So, here's the command. IP route 192.168.1.0, 255.255.255.0, G00. You can type out the whole interface name if you want, or just a shortcut like G00 is fine. Now, before we check the routing table, there is one more option. You can specify both the exit interface and the next hop. So if R2 wants to send packets to the 192.168.4.0/4, G01, because it's to R4. And which interface should it send packets out of to reach R4? G01, because it's connected to R4. And what is the next hop IP address? It's 192.168.24.4, the IP of R4's G00 interface. So here's the command. IP. An interesting point is that when you specify only the exit interface of the static route, it says the destination. An interesting point. Okay, and here is R2's routing table now. You can see how each route is displayed. An interesting point is that when you specify only the exit interface of the static route, it says the destination network is directly connected. Look at the route I've highlighted in blue. 192.168.1.0/24 is directly connected. That network is not directly connected to R2, but that's how it displays in the routing table when you configure only the exit interface. Static routes in which you specify only the exit interface rely on a feature called proxy ARP to function. This is usually not a problem, but generally you can stick to specifying a next hop only, or both exit interface and next hop. Neither configuration method is necessarily better than the others. Just use whichever you prefer. Note that proxy ARP is beyond the scope of the CCNA. I won't spend time explaining it here. However, you should know that, when configuring static routes, you can specify the next hop, the exit interface, or both. I introduced the concept of default routes when explaining how a PC's default gateway works, but let's review. A default route is a route to O.O.O.O/O. /0 means that all bits of the netmask are 0, so none of the bits of the address are fixed. They can all change to be either 0 or 1. So, O.O.O.O/O is the least specific route possible. Its destination IP address, destination IP address. If the router doesn't have any more specific routes that match a packet's destination IP address, the router will forward the packet using the default route. So a default route is often used to direct traffic to the internet. In the network below, R1 is connected to R2 and R3, which are other routers owned by the same business. More specific routes are used for destinations in the internal corporate network, such as destinations connected to R2 and R3. However, traffic to destinations outside of the internal network is sent to the internet using the default route. This isn't the only way to use a default route, but it's a very common use case. Okay, I added some IP addresses to the diagram, and also configured a couple static routes, which I'm not showing here. I then checked R1's routing table. First, notice the part I've highlighted. Gateway of last resort is not set. This means that no default route has been configured yet. Gateway of last resort is another name for default gateway. Now, in R1's routing table, there is a route to 10.0.0.0/8 with R2 as the next hop. And a route to 172.16.0.0/16 with R3 as 8, with R2 as the next hop, and a route to 172.16.0.0/16 with R3 as the next hop. Perhaps these are networks used internally by the company. Now let's tell R1 to send all other traffic to the internet. Here's how to configure a default route.
IP route, this is the address, net mask, and then jump.
The structure of the command is the same as any other static route, but the network and net mask should both be all zeros, O.O.O.O. And that's it. R1 now has a default route. I checked R1's routing table. Let me point out a few things. First, here's the route, O.O.O.O via 203.0.113.2. Notice next to the S code indicating that it's a static route, there is an asterisk. What does that mean? In the code's legend, it says that the asterisk means candidate default. It means this route is a candidate to become the router's default route. It's possible to have multiple candidates. In this case, there's only this one, and here it states, gateway of last resort is 203.0.113. That's all we'll cover about default routes for now. The configuration is the same as a regular static route. Just remember that the network address and net mask are both O.O.O.O. We will use default routes in many future lessons as well, so you'll get more familiar with them throughout the course. Here's what we covered in this video. After that, we use OR's default. Let's go to the following commands configures a default route on a Cisco router.
Default route O.O.O.O. B.
Okay, when configuring a static route O.O.O.O, O.O.O.O, fixed length with it, all 255. Examine R1.
Which interface will it use the bracket distance for 8.8.8? 8.8.8 not matching, so it's directly connected. Two or 3.0.113.2 gigabit Ethernet. Gigabit Ethernet 2. Gigabit Ethernet 2.
One's routing now to think of Gigabit Ethernet 02. The only route that matches destination 8.8.8.8 is the default route. This route doesn't specify an interface, but it does state a next hop of 203.0.113.2. So if you look at the route for 203.0.113.0/24, you'll find it's directly connected to G02. So R1 will send packets destined for 8.8.8.8 to next hop 203.0.113.2 using the G02 interface. Okay, let's go to question 3. Examine the network below. Complete the graph with the answer. That's the each router with .0. Examine the following static route in R1's routing table. What command was used to configure this route?
What command is used to configure this route? IP route. What's the difference between 16? So it's D.
Pause the video. Is D. The route as an a static /16 is a network address. Connected in the is beyond CCNA. Then a technique called proxy ARP is used to find the next hop. Proxy ARP is beyond the scope of the CCNA, but feel free to Google it if you're curious. Okay, let's go to question 5. Examine the diagram below. How many static routes would you have to configure on R3 for it to know all destination networks?
All destination network. How many static routes to configure? Two routes. Two routes. Routes.
Pause the video now to 4 routes. Answer.
4? Wait a minute. 1, 2, 3, 4. Yeah. Okay.
That works. 192.168 all destination 4.quiz and JCNP level channel Jake Pavli Rat and Lucian Stoichitoyu. Sorry if I pronounced your name.
Day 11, part 2. Only 13. For non-hosts like PC to send also the mechanic to its default gateway. A default is a route to a network. The network. Oh. The list specific the default route or 0 o.o.o.o slash 0 default, right? To send a run does return it a route to every network in the path. Does a router need a route to every network in a no? To the destination. Configure a static run. Specify the next hop IP. IP route destination. IP destination network, and then net mask, and then next hop. Configure a static route specifying the exit interface. IP route, IP address, net mask interface. Configure a static route specifying the exit interface and next hop. IP route, IP address, net mask, exit interface, next hop. Code internet static route S. Configure default route specifying the next hop IP. IP route o.o.o.o o.o.o.o next hop IP. Default route is a route to o.o.o.o slash o.o.o.o. Static routes in which you specify only the address directly connected interface. However, if you direct traffic to the internet, default route. Default. In the routing, the gateway of the last resort is not set means no default route. Get default candidate S with asterisk. To send my run, does it return it or no? The runner is the list specific default route. Configure route specifying the next hop. IP route, IP address, net mask, next hop. IP route, IP address, net mask, exit interface. For now, it will send packet to its default gateway. Is in the direct traffic default route. Code candidate default route asterisk. In return, the output gateway is not set. Means a default route is not configured. Static route in which you specify only the place directly connected in access interface. Code get a static route S. Configure a static route specifying exit interface and next hop. IP route, IP address, net mask, exit interface, next hop. Configure default specifying the next hop IP. IP route o.o.o.o slash o.o.o.o next hop IP. A default route is route to o.o.o.o slash o. Good. Cool. Now let's do the lab configuring static route. Configure the PC and routers according to the network diagram, hostname, IP address, etc. You don't have to configure the switch. Okay. config Ethernet configure default gateway 192.168.1.254. Fast Ethernet 192.168.1.1. PC1, okay. You don't configure the switch. Okay, I'll just go to here. En conti hostname R1 and then do show IP interface. Brief. Configure the Ethernet one. So IP INT G01 IP address 192.168.1.254 255.255.255.0. Now shut in G00 IP address 92.168.1.255.255.255.0. Shut. And then sit right sit. Now you're good. Oh wait. Still not configure the routing table. Enable show. En conti hostname R2 and then interface G00 IP address 92.168.2.255.255. IP and G01 IP address 192.168.13.2 255.255.255.0. Right? And shut. R1 is okay, and then now R2. good, 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 good.
Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this lab, we'll get network to host name practice with basic PCs R1 to click 2.168.255.2, but from the CLI. Now, let's 255. Finally, let's enable G00. I'll set the IP address. IP add description. Okay, let's check on the interfaces. Do show IP interface, but G00 is up down. That's not a problem. It's just because R2's G00 interface is still shut down. Now let's go on R2. Interface G255. Okay, let's check. Check on the interfaces. Do show IP interface. 3's interface is still disabled, but enter 3. Set the IP. 192 interface brief. Configure PC2. Click config.25168. Some review. Ping before starting PC2, and then PC2s will have to configure. We need two-way reachability, so people already connected .0s, so H networks R1. Configure the route with this command. It says destination prefix, meaning the network address, which is 192.168.3.0. Use the /24. Next, we can specify the forwarding route 55.255.255.0 since it's /24. Next, we can specify that all of these options are interface types. I'll specify the next hop address and see there is another possible option, distance metric for this route. I'll talk about this option in a later video. One's routing table. You can configure network address to 92.155.2 IP address interface. However, this is a point-to-point interface, meaning it connects only to one other device. This is different than, for example, many routers connected to a single switch, which we would call a shared segment. Anyway, don't worry about that for now. You can just ignore this message. 192.1. Okay, here are the two static 3's static 2.168.255. Let's check the routing table. O to get out of interface config mode. Finally, let's configure R3. Static route 168.255. Let's check the routing table. That's for each interface in command protocol. But 198.3.1 pings should click on desktop, then command prompt. Okay, so this is the moment of truth. The first ping might fail due to ARP, Address Resolution Protocol, but once ARP is finished, the rest of the pings should work if we configured everything correctly. Let's try. Ping 192.168.3.1. Okay, looks like PC1 is able to reach PC2, and PC2 is able to reach... Thank you for watching. Please subscribe to the channel. Like the video, leave a comment, and share the video with